Usually takes only a few seconds. Okay, there it is. Like yesterday, once it took like a whole minute to start the recording. Like, okay. Okay. And since I wasn't recording until just now, I'll just make a note here also for those of you, everyone who reads the notes. Okay. All right. Now, in the other part of this lesson, 3.4a, what we're doing was using the derivative to determine where a function was increasing or decreasing. So as x increases, does the y value increase or decrease? And that is used to what we're going to see in this lesson is actually applying that. So we're going to use whether a function is increasing or decreasing to determine if the function has a minimum or maximum value at a certain point. And that's what the first derivative test is called. It's gonna so when these points happen where the derivative turns out to be zero, in other words, where there's a horizontal tangent, that could mean that the function has a maximum or a minimum value at that point, or it could be neither one. So the first derivative test is used to help determine which one of these it is. And all these, what the actual first derivative test is, and what it means is something I will discuss as we go through the problems. Okay. So what we have here for this function, we want to find critical values of a function. Critical values are where the derivative is equal to zero. There may be more than one depending on the function. So that's the first step in several of these problems. So just remember that critical value is where the point at which the derivative is equal to zero. There's one other possibility. What if the derivative is not defined at that point? As an example, suppose a function has a kink in a graph. So, for instance, it's decreasing, and then there's a sharp corner, and then it continues on from there. So in a situation like that, the derivative at that kink is not defined because there's not a well-defined tangent line, but it's still considered a critical point because there might be a minimum or maximum there. Now, I had to tell you that because that's the actual definition of a critical value. But what we will find in the problem is that it's really the first meaning of a critical value that is one you'll actually encounter in problems, finding where the derivative is equal to zero. We tend to deal with functions that are very nicely behaved in this class, that tend not to have points at which the derivative is undefined. Okay, so that's what we need to do in this case is take a derivative of this function and then set it equal to zero and solve. So first, taking a derivative, so that's just using a power rule or a coefficient rule for the second term that you should all know how to do by now. But then So then we go ahead and set this equal to 0 to find critical values, also known as critical points. So these terms are synonymous. I've even seen them called critical numbers in other calculus textbooks. So, so you can think of critical anything as a point at which the derivative is 0 or undefined. All right, so we go ahead and set the derivative equals 0. So that means that 20x minus 40 is equal to 0. So then you can go for the algebra and move a 40 to the other side. And then just divide by 20, and we get only one critical value, that is x is equal to 2. All right, so once we have that critical value, then we're going to determine if the function f of x has a maximum at this point or a minimum at this point, or maybe it's neither one. And that's what the first derivative test is for. So what we actually do is go through the same motions as from a previous lesson, where you're going to find out, now that you know that the derivative is 0 at x equals 2, the derivative has to be positive or negative everywhere else. So either increasing or decreasing. So you need to sort out which is which. Where is it increasing? Where is it decreasing? So what you do is you choose some x value less than 2. And I mentioned in the previous lesson I like to choose 0 if that's possible, because that's convenient. So we go ahead and plug in x equals 0, and we get into the derivative, and we get the negative value. So that means that f is decreasing for x less than 2. Another way of putting it, using an interval notation you used from we saw in the last lesson. So on the interval minus infinity to 2. Okay. And then we choose another x value that's greater than 2. So again, whatever you like. So 3 in this case. So now we plug that into the derivative, and we get a positive value. So it's increasing for x greater than 2. Or in the interval 2 to infinity. Okay. So this is like what we did in the last lesson. We found out where a function is increasing or decreasing. So now I can tell you, okay. What is the first derivative test? All right, so there are 3 possibilities. So if function f is decreasing for x less than some critical value c, so I'll write that first. If so, if it's decreasing to the left of c, and increasing for x greater than c. So that is f prime changes sign from minus to plus. X equals c. So by virtue of being critical value, either derivative is 0 or not defined there. So there may be a sign change at such a point. Then f has a local minimum at x equals c. Now, what do I mean by a local minimum? That says that f of x is less than or equal to greater or equal to f of c for x near c. So that's where the local comes in. So in other words, the function has dipped. So we have a value, if you will, in the graph. So it's decreasing. It's hit rock bottom, and then it's going up after that. But only near C. And the reason what's meant by local here is that, yes, that is the smallest value of f in that area, but elsewhere in the graph of f, it may hit a lower point. But that has nothing to do with what's going on here at x equals c. So a function could have, if it behaves like this, it could have several local minima or maxima. So the first derivative test is used to determine if a certain point x equals c that's known to be a critical value might be a local minimum or maximum. Now, in the next lesson, 3.5, we'll learn about finding the absolute maximum or minimum of a function. So point that is greater than or less than all values of f on a certain domain. But here we're just looking at what happens nearby. Okay, so the derivative changes sign from minus to plus. That means it's going from, so it's decreasing, then increasing. That's a minimum. Similarly, if it is increasing to the left of C and decreasing to the right of C, so it changes sign from positive to negative. So f is going up and then down. Then that is a local maximum. So we can say that values of f are less than or equal to f of c. And again, local, so only for when considering points nearby. So it may assume a larger value elsewhere. Okay, whenever there's a sign change in the derivative, and as determined by plugging in points less than and greater than c, we can determine if there's a local minimum or maximum. Now, what about the other possibilities? So C is a critical value, and f is increasing on both sides. So you check x values to the left and the right, and you find that it's increasing for both. Or decreasing. So in other words, f prime does not change sign at all. So it may equal 0 at this point. So as an example, like for instance, the function is increasing, and then the graph goes flat at C, and then continues on after that. Then that point is not a maximum or a minimum. All right. So sign change gives you a local extremum, so maximum or minimum. If it does not change sign, then it's not for one of those things. One example, x cubed at x equals 0. Because the derivative is, so x equals 0 is critical value, because the derivative is free x squared, which would be 0 at x equals 0. But free x squared is never negative. So it's positive, positive, then it becomes 0 at 0, and then becomes positive again. And sure enough, x cubed has a graph like I described, something like this, where it's increasing, increasing, stops increasing at that one point, then resumes increasing again. So it's not a local maximum or a minimum. Whereas simple example of like a local minimum would be x squared at x equals 0, because in that case the derivative is 2x. So for x negative, the derivative is negative, and then for x positive, it's positive. So it's going from, so it's a parabola. It's decreasing, decreasing, and then it's increasing again. Okay. Whereas if I can flip this around, for local maximum, I look at the minus x squared. So the graph is turned upside down. So we have a local maximum at x equals 0. Okay, so that's what the first derivative test is all about. That you find a critical value wherever derivative is 0 or undefined. Check how a derivative behaves on either side of that point. If it's one of these sign changes, you need to classify it accordingly as a minimum or maximum. If there's no sign change, then it's neither one. So now we'll try this out okay, so on, sorry, I'm still in the middle of this problem. So what we found here is this function has a critical value at x equal 2, and it was found to be decreasing before x equals 2, and then increasing after that. So what we can conclude, is has a local minimum okay. X equal 2. Why? Because the function changes from decreasing to increasing at 2. Okay, so that's local minimum. Minimum is plural. Okay. Now, what the problem actually asks for in Hawks is, to go back to the wording of it, find any local extrema. So extrema would be a maxima or minima as an ordered pair. So it wants an x value and a y value. The x value we found, that's x equals 2. To get the y value, you have to substitute that x value into the original function. So we go ahead and do that. Whoops, should be a minus there. Okay. And we get minus 40. So that point is where there's a local minimum. So x equals 2, y equals minus 40. All right. So questions about how a first derivative test proceeds. And we're going to show more examples, but any questions at this time? So here we're doing the same thing. Here's our function. Find a critical value, so find a derivative and see where it is equal to 0. So we go ahead and take a derivative just using the basic rules. And now we're going to set this equal to 0. All right, so then we just divide by 6, and we get, once again, only one critical value, and that is x is equal to 8. So now we have to check how a derivative behaves for points away from x equals 8. So for less than 8, is it positive? Is the derivative positive or negative? Is the function increasing or decreasing? So that's what we'll do in the second step. Again, an ordered pair is needed. So once we know x will be 8 if we find any local maximum or minimum, and then we have to plug it into the original function to get the corresponding y value. But first we need to see, is it a max or a min at all? So first we choose something less than 8, and that's before 0 is convenient. So we get a negative value there. So to the left of x equals 8, it is decreasing. They can choose whatever you want greater than 8, so 10. And we get a positive value. So the sign of derivative changes from minus to plus. So it's decreasing, then increasing. Okay. Sorry, I need to check something here. Okay. All right. So because it changes from decreasing to increasing, so it's going down and then going back up. So that is a local minimum at x equals 8. So now to get complete the ordered pair, we substitute that into the original function, into f. Okay. Make sure you plug into the original function f, not the derivative, but f of x. Otherwise, you just get 0. And we get it's 3x squared minus 14x minus 6. All right, and we get minus 198. So that completes the ordered pair. So that's a local minimum at this point. Okay. Now I have a function of a somewhat different sort as far as taking derivatives is concerned, but the task to perform is the same. Okay. So taking a derivative, it's best to rewrite the function. First, 49x plus 81x to the minus 1. That's more conducive to using a power rule. So then when you take the derivative, coefficient rule for 49x just gives you 49. And then we have minus, for the minus 1 coming down, 81 x to the minus 2, but that's the same as 1 over x squared. So that's what we get for derivative in this case. Now, now we set this equal to 0. All right, so then we move 81 over x squared to the other side, and then multiply both sides by x squared to move it up top, and then so then we take the square root of this, and for a problem like this, we're taking square root. Do not forget to take both the positive and negative square root. So we actually have two critical values here. Now, one thing I want to point out is I mentioned earlier that a critical value is a point where the derivative is equal to 0 or undefined. This derivative is undefined at x equals 0 because we'd be dividing by 0. However, I'm not including it as a critical value, and the reason why is f of x itself is also undefined at that point. So to be a critical value, it must be in the domain of the original function. And so if f is defined at a point, but the derivative is not defined at that point, then it's a candidate for a critical value. So critical values must be within the domain of the original function f of x, but in this case, x equals 0 is not. So these are the only critical values that we have, plus and minus 9/7. Okay. So now that we have two critical values, we have three regions to consider. And what you might want to do is, like if you're working this out on paper, draw a number line and mark these points on it. So first mark minus 9/7 to the left and 9/7 to the right. So then you have the three regions to consider is x values less than minus 9/7, and then a point in between these two critical values, and then one is greater than 9/7. Now I can also explain this in terms of intervals, like from a previous lesson. So minus infinity to minus 9/7, minus 9/7 to plus 9/7, and then 9/7 to infinity. Okay. All right, so you can use either perspective, but okay. So now we're going to use the first derivative test to determine whether these critical values are maxima, minima, or neither one. So first I need to choose a point in this interval, something that is less than minus 9/7. And of course, it's always more convenient to choose an integer. So for instance, -1 would not work, but -2 would work. So that's less than minus 9/7. So I'll go ahead and do that. And substitute that into a derivative to see if it's positive or negative. Okay, so then you substitute an x equal to -2, and that gets squared, so we're going to get a positive value down here. So we're going to have so we have a 49 minus 81 over 4, which works out to 115 over 4, so we get a positive value. So in this region, the function is increasing. Now we move to the next region, x between minus 9/7 and 9/7. Now, actually, this one we have to be careful about. Because the original function is undefined at 0. So I need to break it up. The reason why I have to do that is if I pick an x value in here versus in here, it's possible that we may actually get different outcomes. So by checking whether minus 9/7 is a local max or min by looking at these intervals, and then checking if plus 9/7 is a local max or min by looking at these intervals, we can be sure to get a reliable indication. So if a function itself is undefined at a point due to dividing by 0, take it into account when choosing x values. And for this problem, it would turn out to make a difference, but for other functions, it might. So, okay. All right. So I'm going to choose something between minus 9/7 and 0. So I'll choose -1. And when I substitute that into the derivative, all right. So I substituted -1. So I get 49 minus 81 because the minus gets squared also. So we're subtracting something positive. So we get a negative value. So if we're looking at minus 9/7, the derivative changed sign from plus to minus. So it's increasing equal to 0, derivative equals 0, and then the derivative goes negative. So the function is decreasing. So when it's increasing to decreasing, as we see here, then we can conclude that it's a local maximum. Okay. So sign change from plus to minus, maximum. Okay. So now I need to look at plus 9/7, see if that is a local maximum. So I need to choose something between 0 and 9/7. I can choose 1. So go ahead and write it out. And we get a negative value. So to the left of 9/7, it is decreasing. And finally, we need a number greater than 9/7. So I'll just choose 9, just because, and you can choose anything, but things work out particularly nicely in this case. Because I have 49 minus 81 over 9 squared. So the 81 and 81 cancel each other out, and we get a positive value. So the derivative changes sign from minus to plus. So the function is decreasing, then increasing. So that is a minimum. Right. So we have a maximum at minus 9/7, a minimum at plus 9/7. But in both cases, we need ordered pairs. So now you have to substitute both of those values into the original function. So first with minus 9/7, and we get minus 126, and then substituting plus 9/7, and we get plus 126. So we have these ordered pairs that get entered into Hawks. All right. So thing to keep in mind from this problem that if the original function f of x has something like this, something over x, so a function's undefined at a point, and therefore the derivative won't be defined at that point either. But that affects which x values you use to check whether a critical value is a maximum or a minimum. So when you're finding points to plug into the first derivative to check is there a sign change in the derivative, be sure to take points where f is undefined into account so that you won't get a wrong indication. Because the first derivative test is based on x values near the critical value. So it's best to choose something that's fairly close to them, but of course you also want to pick something that's convenient, like an integer. So that's why if I picked x equals 1, that's fine for this critical value, but under the circumstances with this behavior at x equals 0, x equals 1 is a bit too far away to correctly judge the behavior of what's happening at minus 9/7. So again, local maximum, local minimum is about what's happening near the critical value. Questions about what happened in this problem? Okay. Here a function of different sort of a fractional exponent. The task is the same, find the critical values, and then determine if any of those critical values are max or min. All right, so here we're going to use the power rule. So pulling down the 5 halves. So we get minus 20 over 2, so minus 10, x to the 3 halves. And then the coefficient rule gives us 640. Now, it's kind of strange working with this fractional exponent here. In some cases, the numbers still work out nicely, although, of course, chances are you want to go to your calculator for this. So we set the derivative equal to 0, and then when we rearrange, so we get 640 is equal to 10x squared. So, okay. We then divide by 10, so we have 64 equals x to the 3 halves. Okay. So the way you would solve for this is you want to get rid of this, cancel out this fractional exponent to isolate x on the right side. So how you would do that is if you raise both sides to the 2/3 power, so when you have x to a power, but you raise that to a power, you multiply the exponents. So then you have 64 to the 2/3 Okay, where'd it go? Oh, okay. Sorry, I'm puzzled as to why that 2 in parentheses is appearing. I honestly have no idea where it's coming from. Okay. Oh, I see. All right, so x is 64 to the 2/3. Now, yes, you can just go ahead and work that out on your calculator. It does happen to work out nicely in this case because that's the same as 64 raised to the 1/3 power squared. Okay. So if you were to work this out, then you could just square that. Now, this doesn't really mean anything unless you're dealing with a number that happens to be a perfect cube. Can anyone tell me what is the cube root of 64?
Four.
Yeah, it's 4. Because 4 times 4 is 16, times 4 is 64. So what we get is 4 squared is equal to x. So we get 16. Right. So that is the critical value that we have. So yes, you could use your calculator, but now and then in some of these problems, you're dealing with these fractional exponents. You have to choose numbers where things still work out to a nice number. Okay, so now that we have a critical value at x equals 16, we go ahead and check if it's the maximum, minimum, or neither one. Okay, so we go ahead and so we can choose points on either side of 16. So for x less than 16, we can just choose 0. And so we go ahead and substitute that into the derivative, and we're just going to get 640. So we get increasing. All right, so x less than 16, 16, x greater than 16. Okay. So now to pick something greater than 16, you could just use 20. So we go ahead and substitute this in here. And for that, you'd have to use your calculator, and you get this negative value. So what happens is, as at x equals 16, a derivative changes sign from plus to minus. So increasing, then decreasing. So what we have here is a local maximum at this point. All right. Now we need an ordered pair. So now you substitute 16 into the original function. And you need your, actually in this case, numbers work out nicely because you raise 16 to the 1/2 power, that's 4. So then you take, so 16 to the 5/2 is the same as 4 raised to the 5th power. And the result you get is 6155. So that turns out to be the final answer of this ordered pair. X is 16, Y is 6155. Classifies a maximum. Now, on Hawks, you have a box for local maxima, box for local minima. So you'd enter this in the maximum box. The minimum box, you would leave blank and also check none. So there's a radio button for that to indicate that there are no local minima for this function. All right. Next two problems, actually, I'm kind of surprised that these got included in here because they really are no different than problems that appeared in the previous lessons. Because here we're not even dealing with critical values or max or min. It's just a matter of determining where is the function increasing or decreasing. So what I will do is now I will include the solution for number 5. Where you're just taking the derivative, setting it equals 0 to get one critical value, and then you choose numbers less than and greater than it to determine if a function is increasing in this case, because it's positive for x less than 580, and decreasing for x greater than 580. So then you just give your answers open intervals, that it's increasing on the first interval, decreasing on the second. I'll go through, especially in case anybody missed last time, similar kind of problem dealing with, again, increasing or decreasing intervals. This involves a profit function. So you're given a revenue function, you're given a cost function. So revenue minus cost will give the profit function. So we can subtract it off. Be sure to distribute the minus through everything here. So then combining all the like terms that you get, this is your profit function. That's the one you work with. You want to find out where profit is increasing or decreasing. So you go ahead and take the derivative. So we get minus 2 times a half. So we get minus 1 times x, then the plus 54. So now it's particularly easy to see where the derivative is equal to 0. It's just going to be at x equals 54. Now notice the domain of a function is given to be 0 to 90. So take that into account when giving your intervals where it is increasing and decreasing. So you're breaking up this domain at the one critical value, x equals 54. So the intervals to consider that will become part of your final answer somewhere. From 0 to 54, and then from 54 to 90. So you need to pick x values within these intervals. So something less than 54, greater than 54. Okay. All right, so for something in between here, I choose x equal 10 and substitute it into the derivative, and I get a positive value, and then I substitute into something greater than 54 for this interval, and I get a negative value. So you see that it's increasing on the first interval, decreasing on the second. All right. Last problem of the lesson. So here is a given function. Same thing, finding critical values and using that information to determine if we have any local maxima or minima. So now we go ahead and use the power rule and get our derivative here. So we need to see where it is equal to 0. So what I'm going to do is notice that all the coefficients are divisible by 6. So I factor out 6. So then I can just focus on factoring x squared plus x minus 12. Okay. How is this going to factor? It does factor nicely. X plus or minus what?
Plus 4 minus 3.
Yep. X plus 4, x minus 3. Great. All right, so that gives us 2 critical values. X equals 3 from this factor, x equals minus 4 from this one. So now we have 3 intervals to consider for classifying these as max or min, or neither. So less than minus 4, between minus 4 and 3, greater than 3. In this case, the function is not undefined at any point, so we don't have that kind of complication like we did a few problems back. So we just have these 3 intervals to consider. So if I choose something less than minus 4, for example, anything will do. So let's say if we choose minus 10. Okay. Sorry, typos. Right. And then what we get is a positive value, because here we have a negative number, but that's being squared to make it positive, so the whole thing is positive. And then I choose something between these two, so I just pick 0. All right, so we get a positive value first, then a negative value, and then substitute in plus 10, and get a positive value. Now, yes, in most examples, it will alternate, increasing or decreasing. It may not go that way, so again, do not assume that it'll always play out like that. Okay. So the first leftmost critical value, minus 4, is between these 2 points. So since it's going from increasing to decreasing, so up then down, then at that point, that would be a maximum. Okay, so now what you do is you get the ordered pair by substituting minus 4 into the original function, and this is what we get for the y value. So minus 4, 213, that is the first ordered pair that you enter. In the box that Hawks provides for local maxima. Okay. For x equals 3, that's between here and here. So it's minus to plus. So it's decreasing to increasing. So that is a local minimum. So again, you substitute that into the original function to get the y value. So now we have these 2 ordered pairs. So minus 4, 213 goes in the maximum box, and then 3 minus 130 goes into the minimum box. One thing I'll point on a test when you see problems like these. So if I see that, for example, you got the x value correct, like if a critical value, and classified it correctly as a max or a min, but messed up at this stage, if it's and certainly that's something you would still get partial credit for. Um, so, um, so I try to use whatever justification I can to give you at least something. If you got part way through the problem. Okay. All right. So the upshot is take a derivative, find where it's equal to 0, and those are your critical values, which often will be the answer to the first part of a problem. Once you have them, find out how a derivative is behaving near those points by plugging in surrounding x values. That is what the first derivative test is about. So sign change from plus to minus is a local maximum. Sign change from minus to plus is a local minimum. If there's no sign change at all, then it's neither one. All right, so that is how we find a local maximum or minimum of a function. And then on for Monday's lecture, that'll be pre-recorded. You'll see how to find the absolute maximum or minimum of a function. So I've come to the end of our problems. So at this point, you are free to go, but I will stick around for questions. Okay.